それではご来場の皆様、そしてユーストリーム中継をご覧の皆様、大変長らくお待たせいたしました。ただいまより本講演に先立ち、
So before the lecture, we'll be holding a ceremony for the bestowal of a honorary membership to the distinguished Nobel Laureate Dr. Brian
日本
Schmidt.
科学未来館名誉会員顕彰式を執り行います。ブライアン・シュミット先生は、現
Dr.
在
Brian
オ
Schmidt
ーストラリア
is currently
国立大
Professor
学の教授
Emeritus
でいら
of
っしゃ
the
います。
Australian National University.
そして皆さんご存知でしょうか。
And
超新
maybe
星
you
とい
know
う天体を見て、
that he observed the supernova, and through the survey of these objects, he discovered that the university is expanding, and also not only the expansion but the acceleration of the expansion. And honoring such achievements in 2011, he jointly was awarded the Nobel Prize in Physics together with Dr. Adam Riess and Dr. Saul Perlmutter. To honor such achievements, we bestow an honorary membership of Miraikan to Dr. Schmidt today.
それでは、
So
シュミット
may I
先
invite
生、
Dr.
毛利館
Schmidt
長、
and
ス
the
テー
Chief
ジへお上
Executive
がりくだ
Director
さい。
Mori up onto
Professor
the
Schmidt, please
stage.
step to the stage. それではまず日本科
So
学
let
未
me
来館
call
館長
upon the
毛利
Chief
守より
Executive Director
皆
of
様にご挨
Miraikan,
拶申し上げます。
Mr. Mamoru Mori, to say a few words of
皆
greetings
さん
to
こ
you
ん
all.
にちは。ようこそ。
Good afternoon, ladies and gentlemen. Welcome to the Miraikan, the National Museum of Emerging Science and Innovation. I'm really glad to see so many people in the audience gathering here today. Miraikan, as you know, is a place so that everyone can learn the new views about the world and encounter the latest science, and also encounter scientists, authorities in various scientific fields, so as to learn about the latest field of science. And together with all of you, to think about what future we want to create in the future. And so the dream of the scientists are shared with the general audience through our activity. I am really pleased today. I'm very happy today. As was mentioned, the reason is 2 years ago,
本当に宇宙の
for the
根
space,
源
looking into the
の
roots
ことを
of the
理解
space, there was a major discovery that was honored.
ブライアン・シュミット
Dr.
博士が
Brian
来てくださって
has
そ
joined
して
us,
未
who
来
has
館
been
の
honored with the Nobel Prize,
名誉会員に
and
なってい
to
ただける
bestow the honorary membership to Dr. Schmidt. And we are really glad that he kindly accepted
すでに
this
ノーベル賞
membership.
受賞者の方は
The
日本人
Nobel
の方も含め
laureates,
て
including
もう
Japanese
16
laureates,
人ほど
there are about 16 people already are honorary membership to Miraikan in various
一
fields.
昨日は
And 2 days ago,
ノーベル平和賞を
the
受賞
Nobel
され
laureate
た
for peace,
オバマさんにも
President
この名誉
Obama
会
of the
員に
United
なってい
States
た
of
だきました
America also became the honorary member to
本
this
当に私
Miraikan.
はまあ宇
And
宙と
so
非常に
when we talk about
いろんな意
space
味
and the
でワクワクするんで
universe,
すが中
I
で
am
も
always excited on this topic.
今日
But
の
in particular,
レクチャーのタイトルで
today's
ある
title, as
南
you see in the
十字星
title of the
という言
lecture,
葉を聞
the
くと
Southern Cross, the word Southern Cross
普通の人より以上に
is
嬉し
so
く思います
romantic to me,
それは
and more than
私自身が
all of you, I think I'm really excited because
オース
as
ト
for
ラリアに
myself,
大学を卒業してすぐ
immediately after graduation from university, I went to Australia and I
なぜ選んだか
studied at graduate
というと
school there. Why I selected
南十字星が見たかったから
Australia? Because I wanted to see it with my eyes the Southern
そこで
Cross.
初めて
And there, it was the first
地球という
time
のは丸いことが分かり
I
ました
really
日本で見られ
felt
る
to
星っていう
myself
のは
that
限
the
りがあっ
Earth
て
is round. There are
南半
only
球の
a limited
星は見
number
え
of
ない
stars that you can see from
したがって
Japan.
地
You
球は丸い
cannot see
もう
the
一つ
same stars as the southern sky.
余談になるんですけ
And
ども
also, if I may digress a little, according to some rumors, I had heard
北半球では
that in the northern
トイレの水
hemisphere,
は
the water of the toilet
右巻きに回るんですが
will spiral down and flush in the
南
right
半球に回るという
spiral, but in
ことも
northern
確かめたかったんです
hemisphere, it goes around the left rotation. And I
でも
wanted
実際
to
に行って
confirm
みた
that
ら
with my eyes. Of course, when I went to
ど
Australia,
っちにも回るんだという
it
ことが
goes around both
分
ways.
かって非常に単純な発想だったんですが
I was too simplistic, maybe,
改めて
to believe that. rumor, but in any case, science. I encountered a lot of discoveries of science in Australia, so I love Australia. So we have two distinguished scientists from Australia. We're very honored to have them both. But before that, hearing from them, to Dr. Brian Schmidt, Mirai-kan would like to bestow and confer the honorary membership. This card, certificate of the membership, will be presented.
森館長ありがとうございました。
Thank you very much,
では引き続き
Chief Executive
顕彰
Director
状の授与をお願いいたし
Now
ま
the
す。
presentation of the certificate of the honorary membership.
この重々しい
So this is a very heavy
箱はですね、
box that I have. There's a lock to it, a key and a lock and a key.
開けるようになってるんですけども、
With the key,
こ
you
の
open this.
鍵を
And
シュミット博士に
the
お渡
key
しします。
will be handed to Dr. Schmidt. The reason why is that
鍵はですね、
this key,
未来館の1階にあります
on the first floor of Mirai-kan, there's a
ゾーンのとこ
symbol
ろに、今まで
statue
名誉会員の方が
and all of the honorary members
メッセージを
have written down various messages to
私たちが
Mirai-kan
将来
in the past and
次の世代に対して
messages about
何を
the future, what
考
we
えてほしいかという
want
メッセー
them
ジ
to think about, the questions
先ほど
we
ご紹
want
介
the
され
younger
ましたけども
generation to
シュミット
address.
さんは
Dr.
本当に
Schmidt
素晴らしいメッセージをいただいたので、
gave us a wonderful
しか
message.
しその
We're very grateful on this
箱は
occasion. But this
い
box,
つ来られていつ開けて中身も変え
when
て
you
もい
open
い
it,
ですよ
you can open it at any time you wish, and you can change the question at any time you wish. So with this in mind, I would like to hand this key over to Dr. Schmidt. But before that,
そ
Mirai-kan,
の栄誉ある
this honorary membership,
この名誉会員をお送りしたいと思いますので、
I would like to present this membership. This is in English. May I read it in English? Yes,
The
please.
National Museum of Emerging Science and Innovation, Mirai-kan, honorary membership best all for Professor Brian P. Schmidt. The National Museum of Emerging Science and Innovation, Mirai-kan, is privileged to welcome Professor Brian P. Schmidt as an honorary member of Mirai-kan. Professor Brian P. Schmidt, through his distinguished works in the worldwide development of science and technology, has contributed greatly to introducing science as a part of culture. It is in this area that Mirai-kan would like to honor his work and hope to develop further collaboration and support for the future. Mamoru Mori, Chief Executive Director.
森館長、シュミット先生、ありがとうございました。で
Professor
は、そのまま
Schmidt,
しばら
Chief
くお待ち
Executive
くだ
Director
さい。
Moody's, thank you very much. Please wait a while.
Thank ありがとうございました。
Thank you very much.
しばらくお待ちください。
So please give us some time to set up the
どうぞ
stage.
そのままお待ちください。
So please wait for a while.
森館長、ありがとうございま
Thank
した
you。very much.
先ほ
Mr.
ど
Modi,
毛利館長よりお話
as
が
was
ありまし
mentioned
た
earlier,
が、これまで名誉
so
会員になら
far,
れた方々
the
には
honorary
皆さんへの
members
メッセージを
always
問いという形でいた
leave
だいており
us
ます。
a message to you
そし
in
て
the
この
form of
度
a
シ
question.
ュミット先
So we
生
ask
に
the
いただい
Professor
た問い
Schmidt
が今
for
正
his
面のスクリーン
question,
に出てい
which you
る
can
こ
see
ちらな
now
ん
on
で
the
すけれど
screen.
も、Professor Schmidt,
So
please
Professor
read your
Schmidt, could you
message
please
in your
introduce your
prayer words?
message?
Sure. Thank you very much. Although the cosmos are immeasurably vast and complex, building on preceding generations' explorations, humanity has been able to unlock the universe's secrets. What will you discover? Now, I've chosen that message because science and humanity's progress is done by normal people like yourself and like myself, and it's through learning of what people in the past have done and doing our own little part that humanity moves forward. But we will only move forward if each of us does our part to make our own discoveries. Thank you.
Thank you, Professor Schmidt. Schmidt 先生、ありがとうございました。お席にお戻りください。
Please return to your seat.
以上をもちまして検証式を
So this
終了いたします。
concludes the ceremony.
さて、改めまして本日のイベント。
Now,
南十字星の空に
let us start with the event. Exploring the Southern Cross sky through state-of-the-art telescopes, learn about the universe from Australian astronomers. Let me introduce you the panelists.
オーストラリア国立大学教授、2011年ノーベル物理学賞を受賞された
Professor Brian Schmidt, Laureate Fellow at Australian National University and awarded the 2011 Nobel Prize in Physics. And Professor Brian Boyle, Director of Australian Square Kilometre Array SKA Office. Today we are going to hear from both of them the latest results of observational astronomy and the history of the universe and the future. I hope you could have thoughts about these through the talks today. Now, Professor Schmidt, Professor Boyle, please come up to the stage.
Let us give a big round of applause to the two distinguished speakers.
改めまして、ブライアン・シュミット先生、そしてブライアン・ボイル先生です。どうぞよろしくお願いいたします。
Thank you for joining us.
Please be seated. では本日の流れを簡単に皆様にご紹介します。
So, I would like to explain to you how the procedures and proceeding of the symposium. We have two different parts to the symposium for the lecture. First of all, what can you see through the telescope? Of course, there are various objects in the universe. And when you observe the universe through the telescope, what are we able to see and what are we able to learn? That's the second title or second part of the lecture. And of course, this is a good opportunity. There is a big audience here with us today, and we have the two distinguished speakers. So there will be a Q&A session for you to directly engage in questions and answers. So without further ado, we'd like to hear the first talk. What can you see through the telescopes? By the way, I would like to ask the audience, whom among those have the telescope and use the telescope to look at the night sky? Can you raise your hand if you do so?
Thank you. Thank you so much. ありがとうございます。
Thank you.
では専門家が望遠鏡を使ってどんな風に宇宙を観測しているのか、まずはシュミット先生からお話をしていただきましょう。Professor Schmidt, please step forward and begin the presentation.
Thank you very much. It is a pleasure, everyone, to be here to tell you a little bit about what I do in my day job, or my night job, as it turns out to be. So I want to talk to you about observing the universe with optical telescopes. Professor Boyle will tell you about radio telescopes. Now, the first thing I want to give us is a quick tour of the universe. To take a tour of the universe, we're going to use the speed of light as our guide. Light travels at 300,000 kilometers per second. That's 7.5 times around the Earth each second. So now let's look at something that if you come to Australia, you might see in the nighttime sky. That is the nearest star, Alpha Centauri, one of the brightest stars in our sky in Australia. 4.3 light years in distance. Light traveling that many kilometers per second for 4.3 years gets you to the closest star other than our own. To give you a sense of how big that is, imagine in my hand I have a soccer ball. And that's Alpha Centauri. And imagine our sun is another soccer ball. They're about the same size of stars. Think of where that would be. And if you think in Canberra, Australia, where I came from, you'd be about right. That is a scale model of our universe. And what is so remarkable is that if we look out and take a picture of the nighttime sky, using both hemispheres, this is what we see. The Milky Way, our own galaxy of 100 billion stars like our own sun. It's about 100,000 light years across. And if you look closely, and indeed if you come to Australia, you will be able to see the nearest galaxy to our own, a galaxy which we call the Large Magellanic Cloud, which is like the moon in that it orbits the Milky Way. It is a moon of our own galaxy. It only has 10 billion stars in it. Now, I'm going to put a little picture of the moon for scale. And now let's look at a piece of sky that is 1/13 of the entire sky. And we're going to use the Hubble Space Telescope and spend a month looking at that piece of sky. And let's see what we see. So what we see is this. A boring piece of sky filled with 20,000 galaxies like our Milky Way. But we're looking back 12.5 billion years into the past. That's how long it's taken that light to reach us. We are literally seeing well before the Earth was formed. Now that's fairly profound when you think of how big the universe must be. And we can ask the question, how many stars? And that means also how many planets? Because we have learned recently that the average star has a planet. So for every star we count, we can expect there to be at least one planet. So there are 13 million pictures like I just showed you. And each one has 20,000 galaxies in it. If I were to take a picture of the entire sky, then I would count 260 billion galaxies. Each one of those galaxies has 100 billion stars. That means I have a lot of stars and therefore a lot of planets in the universe. How big is that number? Well, the biggest number I can think of here on Earth is how many grains of sand are there on Earth. And the number is not very well known, but it's a lot less than the number of planets in the universe. The universe is very big indeed. Now, if we're going to look even further and with more detail we have a problem. This is what a star looks like in a big telescope. It twinkles. This is twinkling magnified. And it makes things appear blurry. That's why the Hubble Space Telescope is so important. But the Hubble Space Telescope is very expensive to put in space. And our next telescopes we want to put on ground. So how do we overcome that twinkling? Well, we use technology. We make a mirror that is like a contact lens. And that takes out the twinkling about 1,000 times per second. And to do it, we need to make an artificial star with a laser. Now, in Australia and in Japan, we are using this technology to build the next generation of telescopes. And to show you why it's so important, here is a picture of the technology. Here is the planet Uranus. We forget that Uranus has a ring. And that blurriness is caused by this twinkling. And here's what happens when you turn the technology on. The ground-based telescope takes better pictures than you can take with the Hubble telescope because the Hubble telescope is not as big. In Australia, we're developing new technology to use more than one laser at a time, 5 lasers. And that allows us to make bigger and clearer pictures. And we're deploying this on a new generation of telescope we call an extremely large telescope. This is where I work in Australia. It's a very old observatory, which unfortunately burned down in 2003, and allowed us to build a new observatory where we can work on new technology. And that new technology is being used to build a 24-meter telescope, a telescope the size of this room, which will use these lasers to get sharp images of the nighttime sky. Of course, Japan is working on this too. Our telescope will be in the southern hemisphere. Your telescope, the TMT, or 30-meter telescope, will be in Hawaii on Mauna Kea. And together, we will be able to use these telescopes to see the entire sky. We will share our technology as we have in the past, and we will do interesting science. One of the things is to look at planets. Here are the first planets ever seen with an 8-meter telescope. With a larger telescope, you can get even sharper images. And so in the future, we should be able to see planets directly with these new telescopes on a regular basis. And here is a planet in our own solar system, Venus. This is when Venus went in front of the Sun in 2012. And one of the interesting things you see is the sunlight shining through Venus's atmosphere, and that's the ring around the black you can see. That will mean these new telescopes, if they look at a planet like Venus going in front of its star, we will be able to see what its atmosphere is made out of, and perhaps even see signs of life. This is something that will happen in your lifetime, not in the distant future. Of course, we can use the same technology to look at the very distant universe, even further than Hubble, to the dawning of the age of stars and galaxies. about 13.5 billion years ago, when we think the first things in the universe were created out of the sea of hydrogen and helium that was made the time of the Big Bang, 13.8 billion years ago. And we'll explain the Big Bang in my next lecture. Thank you very much.
Thank you, Professor Schmidt. Schmidt 先生、ありがとうございました。さあ、では次に、今皆さん、宇宙にはたくさん明るい星があって、そして惑星もそれ以上にあって、もうゼロがたくさんありすぎて数えられないぐらいということが分かりましたが、このお話を聞くと、皆さんもしかすると明るい星じゃないところに望遠鏡を向けるかもしれません。では次に、ボイル先生に同じく望遠鏡で何が見えるのかお話していただきます。Professor Boyle, please step forward and begin the presentation.
Thank you. It's a pleasure to be here today. Professor Schmidt showed us how exciting optical astronomy was. Radio astronomy gives us a very different but equally important view of the universe. Radio telescopes also look very different to optical telescopes. Radio telescopes detect light whose wavelengths are measured in meters, not millions of meters, as in optical astronomy. The southern hemisphere has an amazing radio sky and some amazing radio telescopes, like the Parkes Radio Telescope, the Australia Telescope Compact Array, and one of the world's newest telescopes, the Australian Square Kilometre Array Pathfinder. In this introduction, I would like to introduce you to some of the wonders of the southern radio sky. In optical astronomy, we get to see a universe full of stars. But even when we look at Alpha Centauri, the nearest star to our own sun, with the most powerful radio telescope on the planet, this is what we see. Nothing. Don't worry, the images get a little bit more exciting later on. In radio astronomy, we don't get to see normal stars, but a universe of gas and dust, the material from which the stars and planets were born. We also get to see exotic physical objects like pulsars and black holes. What happens to stars at the end of their life? Consider this beautiful optical image of the southern sky. You can see the plane of our Milky Way galaxy outlined in the thousands of millions of stars that Professor Schmidt talked about. As you look towards the center of our galaxy, on the right-hand side here, it's overhead in Australia in our evenings right now. You see dark patches of dust between the stars, obscuring the view to the center of the galaxy. Looking above our own galaxy, you can also see two faint smudges. These are the large and the small Magellanic Clouds, only visible from the southern hemisphere, the closest galaxies to our own, a mere 150 billion and 250 billion light years from us. Now look at this radio image of the southern sky. We see the light not from stars, but from gas in our galaxy, distributed in the same Milky Way, or perhaps gassy way, like the stars that were born from this gas. But now look towards the center of our galaxy on the right-hand side. Now there is radio light. Radio waves can see through the dust to the heart of our galaxy, where lies a massive black hole weighing some 2 million times the mass of our sun. But also look above the galaxy and see the plumes of gas revealed in the radio. This is gas from our own Milky Way galaxy that's been torn off by the Magellanic Clouds as these systems perform their hundreds of millions of years orbit around the Milky Way galaxy. From this we can learn not only how stars are born, but also how galaxies form. Radio astronomy can not only help us look at stars and galaxies over scales of hundreds of thousands of light years, but also extreme objects like pulsars on scales of only a few tens of kilometers. A pulsar is what remains after a massive star ends its life in a supernova explosion. After it runs out of nuclear fuel to keep itself burning, the core of a massive star collapses inward due to gravity and blows off its layers in a supernova explosion. In some cases, the core collapse is only stopped when the individual atoms touch, and the mass of the star is now concentrated in a volume only a few tens of kilometers across. At this density, the density of an atomic nucleus, all the material in the star is transformed into neutrons. And 1 teaspoonful of neutron star would weigh 3 million kilograms, or 10 times the mass of every man, woman, and child on this planet in 1 teaspoon. These neutron stars are not only super dense, but as they collapse, their rotation speeds increase. Can I have the video now, please? Wonderful. So just like an ice skater spins faster as they pull their arms in, this also causes the magnetic field in green here to wind up tightly and become very strong. This helps focus the radio waves. We then have a ball of neutrons spinning at up to 1,000 times a second, tens of thousands of kilometers per second, with a magnetic field that's stronger than 5 billion fridge magnets. This produces a tightly focused beam of radio waves, which, like a lighthouse beam, we intercept as the neutron star rotates, with radio pulses, hence the name pulsar, being received at very regular intervals. And I'm now going to play you some sounds of these pulsars, because we can turn these pulsing radio waves into signals. So this is our first pulsar we're listening to. This is the sound of universe from 300 light years away. This is the beam of the pulsar passing by the Earth every second. So imagine I'm a pulsar. Once every second you'll get my light. Next one. This is a pulsar spinning even faster. This is something moving at 10 times a second. And finally, this is a pulsar spinning at 1,000 times a second. Now we can time these radio pulses. They're amongst the most accurate clocks in the universe. In radio astronomy, we can time them to nanosecond, that's a billionth of a second precisions. So we can locate within centimeters the relative position of these objects that are many thousands of light years away. Because of their extreme physical environments, on top of everything else, the gravitational fields are about 100,000 times as strong as our sun's. They can be used to test very accurately the theories of Einstein, Hawking, and others. In one exceptional double pulsar system discovered from over 2,000 pulsars now known in our galaxy, most in the southern hemisphere, the predictions of general relativity have been shown to be 99.95% accurate. A neutron star is, of course, not only the most extreme form of stellar death. If nothing, not even the pressure of the atomic nucleus can withstand gravity, then the star collapses to form a black hole. An object whose gravitational field is so strong that nothing, not even light itself, can escape. Massive black holes are now thought to be present at the center of most galaxies, weighing from a few million to hundreds of millions times the mass of our sun. They are thought to be formed in the early stages of a galaxy's life by the merging of cores left behind by the massive stars that had gone supernova. Once again, radio astronomy provides us with a unique insight into these objects. This image is of Centaurus Ii, a galaxy visible from southern skies, which harbors a black hole weighing some 50 million times the mass of the sun. This black hole, like its much smaller cousin, the pulsar, also produces a beam of radio emission. Only this time, the effect of the beam, seen pink here, illuminates the whole giant galaxy over 1 million light years in extent, 10 times the size of our own. The radio emission from this galaxy, some 11 million light years distant, is so intense that this is the brightest object in the radio sky after the sun and moon. If you went out and you had eyes that you could see the radio, this is the brightest thing apart from the sun you would see, something 11 million light years away. Centaurus Ii is the closest active galaxy to our Milky Way. Understanding how the black hole and the radio waves affect the formation of this galaxy and the countless millions of other galaxies like Centaurus Ii is crucial to understanding the formation of structure in the universe. But despite all these wonders of the southern radio sky, with current radio telescopes, we're still only scratching the surface of the radio universe. All the radio wave energy from all the radio astronomy sources detected over the entire history of radio astronomy still amounts to less energy than a snowflake hitting the ground. To probe deeper into space with radio astronomy requires a massive increase in our ability to collect and analyze these feeble radio waves. Plans to build a next-generation radio telescope, the Square Kilometre Array, to probe back to the first billion years of the universe and to conduct massive cosmic surveys to help understand the nature of dark matter and dark energy will be the subject of my next talk. Thank you.
Thank you, Professor Boyle 先生、ありがとうございました。さて、今のお話で望遠鏡にもいろんな種類があって、
seems that there are many types of telescopes, and Dr. Schmidt has talked about the so-called optical telescope, and you're able to see the skeleton of the universe. And with the radio telescope, you will see the gas and the dust that form such a skeleton. So I have a question to the two distinguished speakers. I think everybody shares the same question. Dr. Schmidt, you can remain seated, please. What is the appropriate condition for observation, do you think, observing the sky? What is the optimum condition?
All right. So we're going to go on to the next talk. Sorry.
Well, I have a question for you.
Okay, yes.
ごめんなさい、英語でちょっと聞きますね。What
I'm going
are
to ask in
the good
English.
conditions to observe with the telescopes?
So for a telescope, in the optical, we need clear skies, like Tokyo has today, but we need calm skies. Skies without turbulence that cause the stars to twinkle. That means we want to be on the top of very tall mountains, like Mount Fuji. But Mount Fuji has lots of snow and rain. So we want those mountains to be on the edge of a desert, surrounded by winds that flow over the ocean. And that turns out to be two very good places on Earth: Mauna Kea on Hawaii, and in Chile in the Atacama Desert, in the mountains of the Andes.
Thank you so much, Mr. Professor Schmidt. ありがとうございました。では、ボイル先生にも聞いてみたいんですが、皆さん、一つ疑問に思ったことがあると思います。
everybody shares the same question as myself. The radio telescope using the radio wave, probably you can use that not only in the night sky, but during the lighter sky during the day.
ボイル先生、
Dr.
お答えいただけます
Boyle,
で
would
しょ
you
うか。
like to respond to that? This is true.
That's absolutely true. Yes, you can use a radio telescope during the day and during the night. I not only have a night job, I have a day job too. Radio astronomers do it all day long and night long. But it is also important, conditions are important. So just like the sun drowns out the faint stars, So we can also drown out faint radio waves. I'll talk a little bit more about that in my next talk, but what do you think is responsible for drowning out the faint radio universe? Turn around and look at the person next to you. That's who stops us from seeing the faint universe, radio universe. We all do. All the equipment we use, mobile phones, cars, all generate radio signals that are billions upon billion times stronger than the feeble radio waves from the universe. So we all prevent ourselves from seeing the faint universe. We have to get away from people, not the sun.
Thank you, Professor Boyle. ありがとうございました。さあでは、
Thank you very much.
次のお話へと参ります。
Now let us move on to the next talk.
こうした望遠鏡を使った観測で、
So, by observing using such telescopes, so what can you find about the universe?
まずはシュミット
First, I would like to invite Professor Schmidt to talk about the accelerating universe. Professor Schmidt, please.
Thank you. So, our story starts in 1916, when a man most of you will not have heard of went through and took the light of a telescope and spread it out into the colors of the rainbow. And he did this not for the sun, but for galaxies. And this man was Vesto Melvin Slipher. And when he did this, he realized that galaxies have this color, which we call a spectrum, that looked like stars. Now, encoded in a spectrum is a fingerprint of the elements that an object is made out of. Every element has a color fingerprint. So he could see that whatever made up galaxies was the same thing that made up stars. And this is, of course, because galaxies are made of stars, something that was not widely appreciated in 1916. But there was one difference. The light of the galaxies of stars was stretched. Light is a wave, and it was stretched redward of the light of our sun. And he knew there was a way to explain this. And we explain it with something called the Doppler shift. If you have a police car or anything, and it's moving, its sound waves are compressed in the direction of motion and stretched if it's moving away from you. This makes the pitch change as an object goes past you, from higher and lower. Light is also a wave, and it turns out that if you compress light waves, they become bluer, and if you stretch light waves, they become redder. So the fact that galaxies' light were stretched indicated that these objects, galaxies, were moving away from us. But why would all of the galaxies be moving away from us? That was a mystery. And it was a mystery solved by measuring their distances. Measuring distances in astronomy is hard. We cannot put a ruler down between us and the nearest star. Instead, we need to rely on how things appear. The further away something is, the fainter it appears. And in 1929, Edwin Hubble used this to look at how bright stars were in the nearest galaxies. And he discovered something remarkable. The faster the galaxy was moving, that is, the more its light was stretched, the fainter its stars were. the further away it was. Here is his data. I always think it's important to show data because it is from data that we actually understand everything we know about the universe. Brighter stars nearby, fainter stars a long ways away. Low velocity, high velocity. The trend, the further away you are, the faster you're moving, caused Hubble to announce to the world in 1929 that this means that the universe is expanding. And why did he say that? Well, he said it because it makes sense. Imagine I have a universe which through the wonders of my computer I can expand. Now let's overlay before and after. What do I see? I see, when I've done that the close objects have only moved a little bit. They would have low velocity. The distant objects, they've moved a lot. Just like Hubble observed, in an expanding universe, the further away you are, the faster you move. And it doesn't matter where you are in the universe, everyone in an expanding universe sees the same thing. Now, we also, in 1917, or 1915 really, we had another revelation, which was Einstein's theory of gravity. In 1907, Einstein had an idea. He had an idea that acceleration due to moving faster and acceleration due to gravity must always be the same. In other words, imagine I put you in a box with no windows. He said there would be no way to tell if I was in a rocket ship going faster or I was just simply on Earth being pulled by gravity. A simple thought that took Einstein 8.5 years to solve. And to solve it, he realized that space needed to be curved. But it allowed him to do things that Newton could not do, like figure out how gravity affected the universe. And when he did this in 1917, he got a shock. The universe, by his equations, should be in motion. But he looked around and he said, I don't think the universe is moving. So he did what theorists always do when their theories don't predict what we see. He added a fudge factor, which we call the cosmological constant. This is energy that is part of the fabric of space itself. It causes gravity to push rather than pull. And so by adding energy to space, he could balance out the pull of gravity. Of course, when it was realized the universe really was expanding in 1929, he described this as his greatest blunder. Now imagine I have a universe which is expanding. Let's run it in reverse. Everything gets closer and closer until a time when everything in the universe is on top of everything else. That is what we call the Big Bang. Now let's think about what that means. Imagine I put on a graph an object's how far apart they are right now. And imagine I run the universe in reverse. That dotted line tells you how fast the universe is expanding now. Then when I run the universe back, when the two objects are of no distance, that's the time of the Big Bang. So measuring how fast the universe is expanding now tells us how old the universe is. I thought this was such an important thing that I figured I should try to answer this question for my PhD thesis. And here I am, 3 years, 11 months, and 4 days after I started showing my PhD supervisor my answer. And that answer? Well, the answer I got was that the universe was about 14 billion years old. Now, the Hubble constant tells us the age of the universe, but it turns out I was cheating a little bit. And that's because that line is straight. Now, what happens if that line is curved because of gravity? Then, if the universe was slowing down due to gravity, everything in the universe pulls on everything else. Then the universe might not be as old as I thought. For a perfectly reasonable amount of gravity, the universe might only be 10 billion years old. But that's younger than what we think the oldest things in the universe are. That would be a problem. And of course, there are profound implications for the future. A universe that's not slowing down is a universe that doesn't have much stuff in it, is a universe that will go on forever, for an infinite time in the future, and expand forever. Whereas a universe that's slowing down, if it's slowing down enough, it will eventually stop expanding and go in reverse. So while both these universes start with the Big Bang, only the second one ends with a Gnab-Gib, which is the Big Bang backwards. Now, I'm glad that joke worked in Japanese. The slowing down of the universe affects how old we think the universe is. It tells us that's interesting. Tells us how old we think the universe is. And it turns out it tells us the future of the universe, and it tells us the shape and weight of the universe. A heavy universe, a universe heavy enough to stop expanding and going in reverse, is a universe that's bent onto itself in a fourth dimension. It's a universe, if I start here and head out this direction, I eventually come back to where I start. Now, if you're having trouble visualizing that, you are not alone. I cannot visualize 4 dimensions any better than you. And indeed, I have never met a sane person who can visualize 4 dimensions. And you do not want to be one of the people who can. A light universe bends away from itself in the shape of a saddle. And then there's the just right universe. The universe that looks and behaves just like you think it should. It has just the right amount of stuff. So, imagine we could measure the universe's past. Imagine we could measure how fast the universe is expanding now and compare it to billions of years ago. Then, if the universe hadn't changed speed, then we know the universe isn't slowing down and is going to expand forever. It's infinite. On the other hand, there's a critical line, that just right line, where if the universe is slowing down faster than that, then gravity will win, and space is finite, and the universe will end in the future. The other side of that line, gravity loses, and the universe goes on forever. What a great experiment. And this is the experiment I was able to start when I moved to Australia in 1994. And the reason I could do it is thanks to these incredibly bright explosions called Type 1a supernovae. These explosions are when a white dwarf reaches a critical mass and explodes as a giant thermonuclear bomb. They are 5 billion times brighter than our sun and create most of the iron in the universe. They're so bright we can see them across the vast universe. But they're very rare. They only occur every several hundred years. And finding them with the new emerging digital technology was hard. Can you spot the exploding star in this picture? Probably not. And we took 1,000 of these images each night. I will show you the exploding star. It's this little guy next to that little galaxy. And the reason I knew that was an exploding star is because we take a before and an after picture. And my computer program would try to find those objects. This object exploded 5 billion years in the universe's past, before the Earth was formed. It shows the power of astronomers to be able to look back through these immense distances and times. So here was our answer that we got 3 years later. Each exploding star gives us a measure of how fast the universe is expanding. The nearby objects, well, you can't really see what's going on, but the distant objects, you can see, don't lie in the bottom part of the diagram down here. When I saw this, I was depressed. I wanted the universe to end. That seemed like a good thing for a universe that started. But then I was more concerned because those objects do not, on average, lie in the yellow part of the diagram, where the universe is slowing down over time. Instead, they were on the top part of the diagram, where the universe was speeding up over time. That was not supposed to be the universe we lived in. It was a big surprise, but it was found by us and another team out of Berkeley at the same time, and it's for that that we won our Nobel Prize. And here is our team that made that discovery, and here is the other team that made the discovery as well, together in Stockholm in 2011. So what is pushing on the universe? Well, that's a hard question. But none other than Einstein gives us an answer. The cosmological constant, his fudge factor, energy that is part of space itself, which we now call dark energy, is the thing that can make gravity push rather than pull. The problem is we need 70% of the universe to be this stuff. And the implications, well, they're quite profound. The universe is speeding up. As the universe speeds up, galaxies become further and further away. And unless the dark energy suddenly disappears, The universe will at an ever-increasing rate expand, fade away, and in the distant future, the light from galaxies we see today will never be able to reach us, meaning that I and my colleagues will be unemployed. Thank you.
Thank you, Professor Schmidt. 清水先生、ありがとうございました。
Thank you very much, Professor Schmidt.
さあ、今、宇宙全般
So
の
we
お
heard
話をいただきま
the
したが、
overall story of the
今度
universe.
は今進んでいる
Now
国際プロジェ
the
クトのお話を
international
していただ
project,
きます。
the progress there will be presented by Dr. Boyle. He'll be talking about the Square Kilometre Array SKA project. Dr. Boyle, please.
Thank you. I left you at the end of my last talk contemplating a large telescope. Well, to see further, radio astronomy needs a bigger telescope. The largest radio telescope on the planet at the moment has a collecting area of 50,000 square meters, the aptly named Very Large Array. But to be able to see radio waves from the furthest reaches of the universe, like Brian can see in the optical, astronomers from around the world are currently designing a telescope with a collecting area not of thousands of square meters, but of 1 million square meters. This is the Square Kilometre Array. It's made up of many thousands to many hundreds of thousands of small antennas. To get a good view of the southern sky and to get away from the radio interference of human activity, the SKA will be located in remote areas, the most radio quiet regions on the planet, in both South Africa and Australia. South Africa will host antennas capable of picking up higher frequency radio waves, whereas Australia will host antennas sensitive to lower radio frequencies. Data will be transferred between the antennas at rates over 10 times greater than the current entire global internet traffic, and combined in a supercomputer 100 times more powerful than the world's most powerful supercomputer today. In 1 minute, the SKA will generate enough information to fill a pile of DVDs 1 kilometer high. In 1 day, it will generate as much information as all the spoken words by humanity ever. The SKA will therefore not only probe the furthest reaches of the universe, but lead the way in the development of computing and information technology in the next decade and beyond. The enormous light grasp of the SKA will allow us to look out deep into the universe, up to over 13 billion light years from us. As Professor Schmidt explained, light takes vast time to travel these vast distances. And I like to think of myself as a cosmic paleontologist. Just like a paleontologist digs back in time through Earth's fossil history, piecing together a history of the evolution of life on Earth by looking at the different rock layers. Astronomers probe further and further back in time the further they look out, and are able to piece together the evolution not of life on Earth, but of the universe itself. Just over 13 billion light years away, or just over 13 billion years ago, about 500 to 800 million years after the Big Bang, is an important time in the universe. You can see in this schematic core sample of the universe here, the first stars appear roughly 500,000 years after the Big Bang. And from there, galaxies start to evolve a few billion years after the Big Bang. The solar system forms 4.5 billion years ago. And finally, we appeared a few 100,000 years ago, and we worked it all out, or so we think. In the radio, we are lucky that the most common element in the universe, hydrogen, the element from which stars and galaxies are largely made, emits energy at the precise radio frequency of 1.4 gigahertz, or 21 centimeters in wavelength. However, the wavelength of the radio emission from hydrogen in the early universe is stretched as it travels over the expanse of the universe. From 21 centimeters in length to 2 meters or more in length, and down from frequencies at 1.4 gigahertz, down through the mobile phone band, aircraft band, down to 100 megahertz or lower, the FM band, as the universe expands. This not only allows us to detect hydrogen back to different times in the universe by simply tuning into a specific frequency, but also demonstrates why we need to put these telescopes far away from human-generated interference, such as cars, mobile phones, microwave ovens, etc. The SKA low-frequency telescope will be able to see the very earliest period in the universe directly by scanning through a range of low frequencies at the FM band, generating the pictures of the first stars switching on and blowing holes in the surrounding interstellar gas some 15 billion years ago. And here's a movie scanning through the FM band, and watch stars, the very first stars, lighting up in the universe. And look at those frequencies. Just think, as you scan your own radio dial, you're also tuning into the universe, somewhere between 13.2 and 13.5 billion years, of course. Of course, there's lots of other signals on your radio dial, and they are many billions of times more powerful. Tokyo FM broadcasts at the same frequency as hydrogen 13.5 billion years ago. So if you could only get rid of Tokyo FM. The SKA will not only be able to reach out to over 13 billion light years, but also be able to study all the galaxies between those far reaches of the universe and our local region of space. Using revolutionary new wide-field radio detectors, the SKA will also be able to identify over 1 billion galaxies, which astronomers will use to map out the large-scale structure of the universe in exquisite detail. Ultra-precise measurements of the distributions and motions of galaxies by this mega-census will make clearer the true nature of dark matter and dark energy that shape our universe that Professor Schmidt described. In particular, we can measure the characteristic sizes of these cosmic ripples, faint distortions in the distributions of galaxies in the pond of space-time, left over by the Big Bang, and see if they change with time. The SKA is in a bit of a race with other optical telescopes to detect this dark energy, or the origin of dark energy, and I rather suspect the optical telescopes will win the race, but who knows? The SKA will also be sufficiently powerful to detect all the pulsars that I described before that are visible in our Milky Way galaxy from the southern sky. This is actually most of them, since the southern hemisphere is much better placed for looking towards the center of our galaxy, where most of those pulsars live. With a large network of these super accurate cosmic clocks, it should be possible to make direct detection of the gravity waves, the ripples in space-time predicted by Einstein as they ripple through our Milky Way galaxy. These waves will cause the pulsars to bob up and down on this wave, just like buoys at sea, minutely changing their positions from Earth by a few centimeters or meters, and hence the highly accurate pulsar clock arrival times at Earth. So detecting a network of pulsars surf on a wave of space-time will reveal the telltale signature of gravity waves. Here again, the SKA is in a bit of a race with gravity wave detectors, but this is one race I think the SKA are going to win. The SKA should also be able to identify the long sought for example of the most extreme relativity laboratory, a pulsar black hole binary pair with which to test Einstein's theory of general relativity to its ultimate limit. Confirming gravity waves predicted by Einstein and the best ever tests of relativity, Einstein would have loved the SKA. Finally, the increased power of the SKA will allow astronomers to increase the space searched for extraterrestrial intelligence by more than a factor of 1 million over existing telescopes. The SKA will be sufficiently sensitive to detect an airport radar or equivalent on a planet 50 light years from Earth. Currently, we know over 100 planetary systems at this distance. And although no Earth-like planets have been definitively confirmed, it's only a matter of time. Just imagine that you, yes you, are the SKA astronomer who first detects signals from another civilization. What would you do? But it is very likely that the greatest discovery that the SKA will make under southern skies is something we can't even imagine at this stage. Just like Professor Schmidt didn't expect to discover an accelerating universe, and talk of dark energy 25 years ago would have had Professor Schmidt considered crazy. Nobody considers you crazy now, Brian. So will the SKA transform our understanding of the universe with something that is currently more fantastic than we can imagine. Radio astronomy, indeed all of astronomy, is set for a very exciting and, I hope, unpredictable future. But it is a future that will be made by the young people in this audience and around the world. And it is a future that will be made by working together across many nations, side by side, under the common sky that we all share. National boundaries become invisible when you look up. So I would like to thank you very much for your time, but I cannot resist leaving you with some beautiful night sky images of the Australian SKA Pathfinder telescope, which is my telescope, under the great outback sky in Australia. I've thoroughly enjoyed my visit. I enjoy all my visits to Japan and Tokyo, and I really hope I would like to extend an invitation to you all to come and visit and see the southern skies for yourself. Thank you very much.
Thank you, Professor Boyle 先生、ありがとうございました。 さあ、それではここからは
Thank you.
会場の皆さんか
Now
ら
we'd like
い
to
ろんな質問
entertain
を
questions
シュミット先生とボイル先生に
to
お答えいただきたいと
Professor
思い
Schmidt
ま
and
す。
Professor Boyle
先生方
from
は
the
座ったま
floor.
まで結構で
You
すの
can
でお答えくださ
remain
い。
seated.
今
So
日は
let's
学
ask
生の
for
方々もたく
questions.
さん
We
い
have
らっ
a
しゃいま
lot
すの
of
で、
young
そういう方々を中
students
心に聞いてまい
present,
りまし
so
ょ
I'd
う。
like to
では、
ask
質問
you
のある
if you
方
have any
は
questions.
大きく手を挙げてく
If
だ
you
さ
have
い。
any questions, please raise your hand.
何の質問でも構いません。宇宙に関係することでも
Any
結構です
questions
し、
about the universe?
皆さんが、はい。では、こちらの3列目の
Yes,
方お願いしま
please.
す。はい。
日本語で構いませんよね。
はい。お願い
So
します。
please allow me to ask a question in Japanese. I actually have two questions. In the wave telescope, you talked about the Tokyo FM.
光での観測だと光が邪魔だっていうのは分かるん
I
ですけど
understand that light may be interfering if you observe using light, but in case of radio telescope,
ものは
eh,
制限した方がいい
this
というのがあるのかないのか
is
教えてい
it,
た
do
だ
you
きたいん
think
です
there must be some restrictions on using the wavelength? And another question is why pulsars emit radio wave? Could you explain to me that very briefly?
Yes, there are international restrictions on broadcasting at certain frequencies. The FM band, of course, is available to radio stations, but it also is an area where radio astronomers want to observe. But rather than stopping the world's radio broadcasts, which we can't do and don't want to do, because I like listening to Tokyo FM too when I'm here, we have to get away to very, very remote places, like the Karoo region in South Africa, or like the Murchison region in Western Australia, because there is where FM broadcasts don't reach. There is where there are sufficiently few people so that their mobile phones, their cars don't disrupt the radio waves. So rather than try to legislate not to have radio emissions, we just go where there are none.
よろしいでしょうか。はい。
Thank
では
you.
次に質問のある方。では一番前の。
Anybody
はい
else? The
この
person in the
お願いいたします
front, the
今マイクを持っていますね。
the lady. Please wait for the microphone.
Is it okay with English? Yes. Like I'd like to ask both of you, as a student, how can the younger generation work towards their dream and succeed in it, like I guess both of you did?
Well, I was your age not that long ago, and all that I can say is you have to just try to do something that you enjoy, whatever that is. And the world tends to do what it does, but for people who work hard and chase their dreams, it's usually pretty nice too. Those are people who tend to succeed. But there are many, many things you can do in life. I never thought I would be able to be an astronomer, but I didn't know what else to do. So I figured if I studied astronomy, I would learn physics, I'd learn math, I'd learn how to program computers, and I knew those three things would all give me a job other than astronomy. I certainly didn't ever think about winning a Nobel Prize, but I followed my dream, figured something would turn out, and something did. That's what each of us need to do. And I can't guarantee how your life will turn out, but you will have many opportunities to do an enormous number of things that are interesting if you do what you do well.
What about you, Professor Boyle?
What a good question. I'm a little bit further away in age from you than Professor Schmidt is, but I can still remember. I wanted to be an astronomer from when I was 8. I didn't think I'd ever make it, but the one thing, I wasn't very smart, and I still am very smart. Everybody I talk to is smarter than I am. But I had passion. And if you have passion and if you have a love of people, and if I can say one thing of Brian, one of the reasons why Brian is so remarkably successful is he brings together teams. He works with people. He loves working with people. And I think if you like working with people, particularly in areas of science, that's absolutely important. It's really a very very tight, very good group dynamic in astronomy. So have passion, love people, enjoy what you do, and you will succeed.
Okay. Thank you so much. ぜひこの会場にいる学生の皆さん、本当に
So I'd like to ask all the young people who are here to try to work hard with passion. Any other questions?
では今度あちらの男性にお願いいたします。
The gentleman in the back.
今宇宙観測での暗黒物質の巡る
observing the universe, I think there is a strong competition of making discoveries about the dark matter. And I want to know whether you are successful in doing that. And also black hole, the predictions of Einstein about black hole. But was that actually discovered and found or not? And if that is discovered, could you tell me where that is located?
So, dark matter remains a mystery. People in several different ways see that it must be there. That is, stuff that has gravity that pulls, like atoms, but is invisible. The problem is that the reason it's invisible is because it passes right through itself and through our bodies, and through our Earth, and it's very hard to see something that never interacts with anything. Nonetheless, groups around the world are trying to look for the very rare times it might interact. But as of yet, they haven't discovered anything. It is my hope in the next decade or so that we will probably get a sense of what dark matter is, if it is a particle like the particles that we know of in our standard model that the Higgs boson discovery has sort of finalized. The question of black holes is an interesting one. It is very difficult to prove the existence of something you cannot see. But we can infer, for example, in the middle of our Milky Way, from stars that orbit something we cannot see, that there is something the size, not much bigger than our solar system, that weighs 3 to 4 million times the mass of our sun. And we know of nothing other than a black hole that we can make that weighs so much in such a small area. So we might eventually be able to see the shadow of a black hole with something like the Square Kilometre Array, but we haven't been able to do that yet.
ありがとうございます。
Thank you very much. So at this time, Dr. Schmidt and Dr. Boyle,
会場の皆様に一言メッセージをいた
your
だきたいと
final
思います
message to the
が、
audience, please.
それではシュミット先生、
Starting from Dr. Schmidt,
よろしくお願いします。
any final comments or messages?
So the astronomy is one area of science and technology. And one question some of you might ask is, why do we do astronomy? Certainly, the politicians in Australia ask me this question all the time. And one answer is because it's interesting. But the reason why we spend so much money doing it is because it's useful. The internet, Wi-Fi, digital detectors that we have in our phones are all things that have involved astronomy and astronomers. Wi-Fi was actually invented by an Australian radio astronomer. That was not his intent. It is not why we did the radio astronomy, but it's something that happened. And so it's important to do things like astronomy, which capture our imagination, give us the passion to do things where we don't know the answer, so that we can learn new things. And that, I think, is why we do astronomy.
Thank you, Professor Schmidt. Dr.
Boyle, please.
It's always a very hard job to follow Brian Schmidt. But I think Brian's really summed it up very well. I'd add one important thing, as well as the internet, as well as mobile phones. The reason I do astronomy is because of you. It's because on a Saturday afternoon I can turn up to wonderful organizations like Marican, see inquiring minds, happy faces, and then give a lecture to a packed house of 300 people. It's inspiring the awe and wonder of the majesty of the universe in all of you, and that you want to listen to this. I'm incredibly privileged and lucky to be an astronomer, and these are the moments when I feel the most privileged and the most lucky. Thank you for that.
Thank you very much.
So all of you to be able to visit Australia someday and to see by yourselves the Southern Cross. Now this concludes today's seminar, Exploring the Southern Cross Sky through State-of-the-Art Telescopes. Professor Brian Schmidt from Australian National University and Professor Brian Boyle from Australian Square Kilometre Array. Thank you very much.
From 4:30
at the symbol zone first floor, there will be a circus science show by the Australian Quest Institute, and also Professor Brian Schmidt's question, what do you discover, will also be displayed on the symbol zone on the first floor. Please submit your questionnaire sheet, and also please make sure to return the simultaneous rotation receivers. Thank you very much for your participation. And also thank you very much for participating in the Ustream broadcast.